So hi, good morning, everyone. You may know me. I'm Elad Wind, and I've been with TAP since day one, together with Totan, whom I'm about to introduce and kick off this day. We're going to have 8 sessions today on covering all work streams and all activities that we have currently working with the Time Appliance project, and some into the future of what we're going to look, what's 2022 going to look like in terms of timing and the developments we plan. Without further ado, this is Dotan Levy. He's the founder of TAP, an architect at NVIDIA, and he's going to take the first session today. Thanks.
Hello, everyone. What we're going to do today in the next 21 minutes or so is, I call it time compression. We're going to take experience of 2 years and squeeze it into 20 minutes. Because if we go back 2 years ago, we had a huge challenge to deploy the largest scale PTP data center. Millions of nodes all synced up, connected with a PTP clock tree, with reliability, with some assurance, and guaranteed error bound. And that was quite a challenge. So we identified few of the challenges on day one. Some of them is the lack of open source equipment for grandmaster, which is the source of time in clock trees. As you know, data centers rely on security and openness, and these open source community is a fundamental part for those. So this was something that we missed. Second thing that we missed is a profile, a PTP profile. The third thing that we need to do is how to scale up. And of course, the PTP expert would say that the answer is a boundary clock. We're going to figure out what happened to that. And last but not least, in data center, we identified on day one that more important than the accuracy is the, what we say, reliability or observability. In a data center, you must know immediately if one of your clock is out of sync, because the application is relying on the fact that the timestamp is accurate within some known error bound. And if it's not, that's a silent data corruption, as we say. The data is not valid, and the application wouldn't know about it. This is a clear no-go. So we needed to build something that will last. And the problem is that if you are familiar with PTP, the PTP clients that doing the measurement live is only measuring the error between the ordinary clock and his own leader, as in his own master. So if we have a clock tree, we don't know the total error between the grandmaster clock and the last one ordinary clock in the chain. So this is a problem that we needed to solve again. And a lot of technical issues in between, of course. And let's start the journey. So, and then we got a few months after we started an unexpected challenge. We were going to deploy the largest PTP cluster worldwide, but on an existing one, with an existing hardware and existing software. And this is not something that we could ignore. And it appears that there is no support for boundary clock. There was a technical problem to add those boundary clocks into the switches. It would introduce a massive amount of testing and some instability to that data center. And that was some kind of, I would say, a point that changed the entire project direction. And without explaining all the way what happened, we just decided to go with transparent clock. But in order to go with transparent clock, it also means that our grandmaster clock needs to take care of hundreds of thousands of ordinary clocks, because there is no one that would scale them. The topology in Facebook data center is known. It's going to be described in later on session. But the PTP Grandmaster should be fed into the SSW layer and then go all the way down to the servers at the end, after the spine and the leaf level and so on. Another thing that is that in those data center, multicast is not something that you can rely on. And we needed to add to all of this multicasting. So if you thought that building a huge scale Grandmaster with a multicast is a challenge, try to think about it with a unicast. A Grandmaster that sends 24 millions of sync messages every second in a reliable way with accurate timestamping, handling all those sessions. Lucky for me, I was gifted with a talented team that doesn't break and doesn't fear from any challenge, and every challenge seems like an opportunity. So instead of boundary clock, we introduced a transparent clock, and that disadvantage became an advantage. Why? Because now the Grandmaster communicates directly with the ordinary clock, and the measurement of the ordinary clock imply the total error bound of this node. So there is no need to find new ways to calculate dynamically the error bound of the entire cluster. Each node can measure its own, and we have a reliability. We got lucky. Now, the nice thing that enables all that is what we called open time server. Again, we had 3 different challenges. One, the Grandmaster was the domain of small companies with hardware appliances, with closed software, nothing upstream, and no common roadmap. So each company has its own feature. This is a problem for a data center operational team. And we decided to rely on those commodity NICs. Commodity NICs comes today with a good capability of timestamping, and they can process hundreds of millions of packets per second and accompany an accurate timestamp with that. So we're going to rely on those commodity NICs, on the commodity servers, and the missing part was the time card, which we're going to have a session afterward that will tell you all about it. But this is actually bring the source of time into the NIC. So the NIC gets a source of time from an element called time card. This is the only new hardware piece in the puzzle, by the way, for this entire project. And the NIC convert this time information into a Grandmaster using a scalable software that was built in a very fast way by Facebook engineers. And there we ended up with rich and open source software that handled the Grandmaster. We envisioned to go up to hundreds of thousands of nodes per Grandmaster, maybe 200s. We were surprised to get the outcome of above 1 million ordinary clock that a single Grandmaster would serve. So without major investment in hardware, the entire cluster got a very good redundancy scheme that few Grandmaster can serve the entire data center and also have some redundancy. And this is a worldwide synchronization that happens with those open time servers. And then the hardware missing element was open up under OCP, and any vendor could come and make his own time card according to our specification and enable a data center usage of that. Even NVIDIA ourselves, we got a small version, a lightweight version of a time card on the top of one of our NICs. So you have a favor of choice between stability and price. It works in a huge scale. We have a very good observability on the error bound, as each node can measure immediately his own error bound. We made very minimal changes to the existing deployment. This is one of the major key to success. In order to deploy in such huge scale, you need every small change that you do needs to be introduced slowly and carefully with test environment, step by step. The first thing that we did, by the way, with that comment is to deploy the software without the hardware. So the software would run on the live production without anything underneath, just to see that there are no security things and the operational hiccups that comes on the way. We did everything step by step. Unicasting, those NICs, they don't care about unicast or multicast. The NIC send 250 million packets per second. That's quite a decent amount of timestamping to serve 1 million ordinary clocks. If you understand the PTP profile that exists, 64 syncs per messages, sync per second for every ordinary clock is more than enough. That brings us to 64 million packets per second. It's no way even near the limit of the network adapter. The issue was with the software, and the Facebook team built a PTP software stack that could scale up. Anything that I missed?
I want to ask a question.
Okay.
Which will lead you to the next one. Am I on? Thanks. So the quick question, if you can go back to the previous slide, Dotan, would that design or with that references and know-hows that we have collected through the past year, the voyage we have taken with Facebook, are they applicable to your everyday enterprise or your other hyperscalers? Or, let's not look at scale. Is that reference design ready or applicable to the ones who are looking to add PTP into their data centers?
So that's a very good question, and indeed, we work with a lot of cloud providers, and every data center is built differently. But I think that given the fact that the changes that we made in this project are minimal to the existing deployment, adopting this model would be the easiest path. I mean, adding a transparent clock into the switches, taking and building those grandmaster appliances which are commodity, and they not have to be a wide deployment, just a few of them in a data center. That's the minimal changes that we think is needed. All the software is open. We do see that some of the cloud provider would need variation of that, and that could be adjusted because in each period of the project, we have few choices to make. And it's not that we came up with just one option. We always had an option A, an option B. So there could be variation, and in top, we are endorsing those suggestions if someone thinks he can increase the spec coverage and offer modification and changes, and we are willing to discuss, and we are completely open about it, like the culture of this entire organization. Did I answer your question, Elad?
Thank you.
Yes. Another thing that we want to mention is that we found out that Linux is supporting well PTP. So this time could be introduced into the application and utilized and actually have a massive cost reduction. The public success that we can share with Facebook is the 3x acceleration of a huge application called Synapse, which is the distributed database. But trust me, there are plenty more applications that could leverage this time synchronization. This was just the first one. But we also found out that some OS are missing the support for a PTP. And the solution for that, at the moment, it's not finalized yet, but the direction that we are taking, and the call for action is to speak up if you see any issues with that, like anything we do in TAP, is to conceal the entire PTP stack in the smart NIC. And that would give you some flexibility towards the operation system. So the ordinary clocks, PTP stack would be all implemented in the Linux running on this smart NIC. So you have OS agnostic PTP deployment. And as we know, smart NICs and NVIDIA DPUs are the future, the vehicles that we target for the next generation data centers. We haven't concluded all our challenges yet. So we identified a lot of problems. We solved the minimum set to deployment, and we have a long way to go. I will mention some challenges, and the call for action is to you to come and join us, contribute your part, even just listen and learn. I'm still learning every day. We meet every other Wednesday. And some of the challenges that we want to attack right now is the classification of oscillators. This is a workstream led by our friend Gary. And you are all welcome to join and contribute your part. We have the security aspect. We want to make the time service in a data center heavily secured. This time server is a service that is done by the infrastructure, and it must be secured in the state-of-the-art tools. We want to introduce more capabilities of the hardware clock into the application. The clock doesn't reflect just his time. It can reflect his error bound. It can reflect his last synchronization point of view. An application could utilize it very smartly. This is a new workstream just announced and will be led by Google team. This is our current workstream, and it's not the last word, as we say. The open time server is live and kicking. There is already a few releases. Everything is open from software to the hardware, and we are accepting any comments. Actually, we have been approached by enterprise owners that want to deploy this specific recipe for PTP in their enterprise. We have a profile defined by Michelle. That's workstream number 2, and that's also an ongoing effort. Again, unicast, scalable, PTP profile for a data center.
6 and 7.
We have the precision time API that I mentioned, led by Google. We have the oscillator that is led by Gary, and a new thing, which is the PTP servos. One of the nice things in PTP or in some implementation of PTP, like this one, the hardware gives you the accuracy, but the software gives you the flexibility and the wisdom. And the servo algorithm, we expect and intend to enrich the Linux open source PTP that they would match the state-of-the-art servos that exist today, and we'll able to give you a better stability, better feature set, failover, holdover, all those things that we want to have from our time service. This is all part of this PTP servo. And number 6 is for you to come and suggest what else can be added into that project. So again, the major call for action is come, join, listen, learn, contribute if you can. This is I think that in the last 2 years I saw a great power of community with that project. We had a very professional forum gathering every Wednesday and sharing ideas. We have lightning talks by the leaders of time synchronization in this market, all the way from physics to data center application, and it's really interesting. And again, I think that given the obstacle that we had in this project, I think that there is a good opportunity, there is a good chance that we will see more and more deployments like this, because this was not the easiest one, if I would say that. This was not the easiest data center to deploy with, and I think that that could be an advantage point. Any questions from the crowd?
You talked about 64 packets per second as an overkill.
Yeah.
Is there a specific rate that is the optimal rate that you can see?
So the optimum, it depends, of course, on three elements. What is the question is, what is the optimum sync rate for a PTP cluster? So, of course, the biggest data point is what is your trade-off point between accuracy and cost. Second is what is your oscillator capabilities, because between those syncs, messages, and also with the fact that the smart servo will remove some of them because of outliers, you will need to be stable. So far, we think that 16 are quite enough for a data center. We don't see any reason to go higher, but there is a capability in our lab. We go all the way up to 64.
Okay, thanks.
Okay. Thank you all for listening. I am very glad to be part of this amazing project. I'm looking forward to collaborate with more people in this industry. I think we broke a lot of boundaries. I think I was happy to have a talented team from Facebook and NVIDIA and SciTime. So thank you all.